We'll get started. So welcome everyone. It is great to see you and exciting to be back for the second substantive component or lecture of this or session of this course. Just to remind us, we are making our way through chapter 1. And with chapter 1, last time we had discussed some of the basic concepts associated with categories, right? And we had placed up on the whiteboard in a rather impromptu fashion a set of examples of categories, which illustrated their basic elements of their definition: presence of objects, the presence of morphisms, the ability to encode structure by specifying for any two end-to-end morphisms, the composition of those morphisms. For any two end-to-end morphisms, there has to be some arrow that represents their composition. So if we have F and G here, there has to be an H going from the source of F to the target of Y here. And then there's axioms of unitality, which says that for each object, I should have noted that there's an identity morphism for that object, which does nothing, where the exact meaning of does nothing will differ a little bit by the category, the specific meaning of that, but they all have this flavor of doing nothing. It could mean multiplying by an identity matrix. In some cases, it may mean going nowhere and staying at the same node on the current graph, right? Going on a path of length 0, for example. It might be something where we're saying 3 divides 3 or 6 divides 6, that a number divides itself. It could be an indication that a given number is less than or equal to itself. That's another form of identity morphism. So the specific interpretation of it differs by context, but in all categories, every object will have an identity morphism. And the first axiom, that of unitality, says the identity morphism composed with any other morphism gives that other morphism back. It says if we have an identity on an object X, call it ID sub X, and then we compose it. Okay, now I'm in trouble because I didn't have F going out of X. If we have an X and we have an F going out of X, if we compose the identity morphism on X, which we traditionally don't even draw because it's always there, we compose it with F. We do ID X and then F, it's the same as F. Or going F and then if F goes from X to Y and doing identity on Y, we compose those two. It's the same as Y. Remember, any two end-to-end arrows have to have a composite. We have F and G in this sort of way. There has to be a composite. And what this is saying is the composite of any morphism with the identity on the source object of that morphism or on the target object of the morphism is the same as the morphism itself. That's one of the axioms. And what's the other one? Can anyone say? What's the other axiom that has to hold for any category? Associativity. Yeah. So if we have a series of 3 morphisms, F and then G and then H, we don't have to worry where to put the parentheses. So F and then G, that gives a composite morphism. And then H, that'll bring us all the way over here to Z, right? From F goes W to X, G goes to X to Y. And then if we compose those, you get something from W to Y. When composed with H, you get Z. That would be like in parentheses F and then G, and then the whole quantity in parentheses, then composed with H is the same as F and then quantity in parentheses G and then H, right? G and then H is some particular morphism from, well, G goes X to Y, H goes Y to Z. They're two end-to-end ones. So their composite will go X to Z, right? And if we have F and then that composite, it's the same as going this composite and then Z, right? The parentheses don't matter. We just can write F and then G and then H without worrying which goes first, which of the composites go first, the compositions go first. And we could write it like this, in this commuting triangle, put a check mark to show that it's commuting, that either way you go around, commuting square, either way you go around the square from W to Z, you normally are able to always find a starting point and an end point. No matter which way we go around, we'll get the same thing. So that's just stating what I said in a commuting square form. So that's associativity. And we know that associativity is something we take for granted in a lot of contexts, right? If we have a list of integers and we append to it, call it F. We have another one, we append to it, call it G. And another one, we append to it, call it H. We know almost in our bones, it doesn't matter whether we do F and append G and then append H, or whether we append G to H and then stick that at the end of F. It's going to be the same. Same thing with string concatenation, right? If we're concatenating foobar and baz, we almost know in our bones that we could do foobar first, kind of compose these two, and then baz, or we could do foo and then the composite of bar and baz. And it's going to get the same thing. We're going to get foobar baz, right? We talked about that last time. So those were the properties of a category. But just like the identity morphism or composition has different interpretations for different particular categories, we have this wonderful profusion of different particulars of categories. Categories can mean very different things. And I gave you a bunch of examples of categories last time, in large part to convey the diversity of them and to try to disabuse any notion that one settles into that, for example, a morphism is always a mapping or is always a kind of a function-like thing. It isn't always. Could anyone here give me, online or in person, give me an example of a category where a morphism is not a mapping? It's not a like takes this in and produces another thing, where it's more of a relation.
When you're
the one that we discussed last time was less than or equal to.
Less than or equal to, yeah.
It's a subset of.
That's right. Is a subset of, it would be another great one. Larissa, were you saying something?
I was going to say the subset of one.
Yeah, subset of is a great one.
Larissa and I are on the same wavelength.
Yeah. Another one where an arrow means divides by, right? It's not like take like this arrow from 3 to 6. I don't know what this arrow from 3 to 5. Why is an arrow from 3 to 5? There shouldn't be an arrow from 3 to 5. That doesn't make sense. There should be arrow from 1 to 5, but 3 to 6, that doesn't mean it like takes 3 in as input, it puts out 6. No, it's a relation between the two, right? And others, yeah. And so we'll see this emphasized even further today. So that was a little bit of review from last time. Any questions about that before we get into some more categories? Well, one of them we talked about was set. Remember that? We talked about set. Remember we had the set of, in Larissa's honor, elephant and flower and smiley face and 0 and 0, 5, 10, etc. Remember these sets? What are the morphisms? So when you approach a category, people get to a beginner might get distracted by what the objects are, but the more important thing is what are the morphisms? You even read a subsection in this book where in a characteristic way, Daniel Rosiak reflects philosophically in the philosophy of no objects, that it's possible to have essentially no distinguished objects for a category and still have a meaningful category, because it's the morphisms that are the interesting things. It's the morphisms, the rules for composition that encode structure. So, can you give me some sense of what are the morphisms in the category set? Function. The objects are sets, or for fin set, they're finite sets. For skeleton, a fin set. There are also finite sets, but there's only one. We've collapsed all the isomorphic ones, all the ones of the same size into one. One of size 2, one of size 3, one of size 4, right? And often I find category theorists often call that fin set, the skeleton of fin set. They just describe the fin set because it's basically the same. They consider things that are isomorphic essentially the same. It's a rose by any other name. Potato, potato, tomato, tomato. It's the same thing. So they consider it essentially it's fin set. Okay, so we saw there are. I gave reference to the fact there are many set-like categories, many things with sort of souped-up sets with extra structure. And I told you last time, but I didn't have a good illustration of it. And I really should have taken this illustration from Eugenia Chang's amazing book, Joy of Abstraction. These are two sets. Guess what sets they are? Sets of size what? 2 and 3. And the point of this that I want to communicate here is that there's no structure. They're just bags of dots. Yeah, there's no, yes, they're concrete categories. Excellent, as called in this book. There's no like one is bigger than the other, or one's a co-product of the others, or one's like the best one in terms of the biggest or the smallest or the irreducible one. There's no structure. They're just bags of dots. Now, what this means, it turns out, is that set has this incredible number from any one set to another set. It has all these different functions. So you tell me, I mean, I want you to go through this in your mind. How many functions are there, distinct functions, mapping from 3 to 2? So going from this to this. But to be clear, remember what a function has to do. For each and every element in the source, function operates on sets, right? I'm using that specifically. I'm not using the general term morphism, which is not specific to function. I'm talking about a function. So if it takes this set for each and every one of the elements in the source, each and every one, it has to assign one particular value for this. So how many distinct functions are there from these 3, from the set of 3 elements to the set of 2 elements? From 3 to 2?
All possible functions?
Yeah, all possible functions.
8.
How many? How many?
8.
8.
8.
8 is exactly right. There's this one could go to either that one or that one. That's it. So if we consider the set of all possible functions, well, we have to make that choice between those two. We have to make the choice between which this goes to, and we have to make the choice between what this one goes to, right? 2 times 2 times 2, or 8, right? Right? And I will note that reflects the fact that the lack of structure here, right? Like, it's not like because this one went to that one, this one also has to go to that one or anything. The fact that there's no structure gives us total freedom in how we map this to these two, either of those two, this to either of those two, this to either of those two. There's no constraints. You get that point? There's no structure here to worry about constraining us. There's no structure we have to preserve. And this is a key point I want to make today. that I went light on last time. How many maps are there from this one to this one? So from the 2-element set to the 3-element set. 9. This first one could go at any of these 3. And the second one, again, it's totally independent, right? It could go to any of the 3 because there's no structure, none. So what you're starting to hear is that, like, when it comes to set, the functions, there's just this wonderful freedom and proliferation of them because there's no structure to preserve. There's nothing that we have to worry about that constrains our mappings, right? And in general, we're going to see the more structure we have when we introduce structure, so they're sets with structure, which we're going to see quite a lot, then we are going to have more constraints. We're not going to be able to just propose any mapping, right? Here we could propose any mapping, right? It could scramble. It doesn't have to worry. This one went to that one, so this one has to go to that one too. No, it just can scramble them around, right? The set has no structure. Are we comfortable with that idea? Okay, so the category, so I'm trying to nudge you up to the next level, which I deliberately tried to avoid last time, where possible. But I want to start bringing you up to this other level. I did a little bit of this. Okay, so we've said that maps between these things, they look a little bit like this, right? Right? We would call this map a function because it maps each and everything here to exactly one thing here, right? It has to. Okay. Is this, so just to review these terms, because I will use them from time, is this, in functions, we speak about injective functions versus, and surjective functions. Does anyone remember what an injective function is? Okay, one by one, but they map it in ways that are well, okay. I'm hearing some good ideas. One by one, there are these terms that are sometimes used for these things that I just want to unpack them for people. What it means is there's no clashes between, like 2 and 3 here map to B. Is this an injective function? No, because these both map to the same thing here. You got that? If 3 instead mapped to C, would it be injective? Yes. And it'll be as if X is a subset picking out a subset of Y. We will call it, does anyone know the word in category theory we use for that? It's a generalization of the notion of an injective function that applies to any to morphisms in any category. There's a special word we use that means it's a subpart of something else. It's begins with M. Monomorphism. And it's monic. It's monic. It's a monomorphism. And for functions, a monic morphism is an injective function. There's another one that we pay attention to called a surjective function, right? And that's one that hits all of these targets, all of them. And a rough, so this one is a little bit more tricky to translate uniquely into category theory speak, but it's very closely related to the notion of an epimorphism, okay? But there's actually a thing called a split epimorphism that's, I think, closer to that. Okay, so just be aware, when you say monomorphism, we mean it's like a sub piece. Here, if 1, 2, 3 went to like A, B, and C, or went to A, C, and D, it'll be like this picks out a subset because there's no clashes. It's like each of these is picking on a certain one of those. It functions as a subset of this through this monomorphism. Okay, so if we put this into a category, we would see these objects, and we would see maps between them like is even that might classify whether each of a set of integers is even, right? Or we could have an is negative map that maps to true and false, right? For each of these numbers, it maps to true or false. Are we good with this notion? So the objects are sets, and x, y are functions from set x to set y. And in the book, there's quite some discussion about size issues that I'm not going to go into, but as some of you will know from Russell's paradox, you can't talk about the set of all sets. And so we talk about a class of sets, for example. But if we deal with fin set, we sidestep all those issues. We're dealing with sets of finite size. So we're never going to have one of them that we have to ask, does it contain all the other sets in it? No, they have to be finite because there's an infinite number of those finite size sets, right? In fin set. Okay. And there's some comments there on what does large mean? What does small mean? What does locally small mean? You can look at. Okay. But we also talked last time about a preorder category where objects are sets, right? These are sets, yeah. And morphisms are indications of whether one is a subset of another, not necessarily a proper subset, but whether it's contained in, whether it's, a subset or equivalent to this other. So is 1, 3 a subset of 1, 2, 3? Yeah, is 2, 3 a subset of 1, 2, 3? So what is composition here? Right. So do you remember the term I used? There's a certain term we use for categories like this, where between any two objects, there's either 0 or 1 morphisms. Remember what it was? I gave 2 terms for it. Thin, and flat. This is flat. They're not like a whole stack of them sticking on top of each other, right? Flat. Okay. So here, there's only one possible morphism, from any object to any other object is 0 or 1, right? And if there's multiple paths, they all commute. There's only one, right? So from 1, 3 to 0, 1, 2, 3, we have several ways of getting there. This way or this way. So 1, 3 to 1, 2, 3 to 0, 1, 2, 3, or 1, 3 to 0, 1, 3 to 0, 1, 2, 3. But either of those ways, it just means there's that 1, 3 is a subset of 0, 1, 2, 3. It's not like it's a subset in different, totally different ways. No. Are we comfortable with this? What's identity morphism here? Sorry?
Each set is a subset of the set.
Each set is a subset of itself. Yeah. Are we good with this? Jeff, are you feeling good about it? Okay. Here's division by 30, division, there's an arrow from the objects are natural numbers, and there's an object, there's a morphism, numbers 1 and above, and there's a morphism from one to the other, from A to B, if A evenly divides B. Integer number of times, right? Yeah. Even, it's an even divides it. Okay. So, okay. I want to take you up a level at thinking about this. We've been talking about specific categories. And now I want to take you up a level that was whispered about last time. And actually, we showed it, like was said. But we're going to need to start getting used to it with things other than set or fin set. Set and its close cousin. So we're going to be starting to talk about categories where the objects, just dots, represent a certain type of structure. We did this already. We talked for sets, right? This dot might represent one set. This dot might represent another set. But here, each of these sets is going to be a preorder. This is a preorder, okay? It's called a preorder, meaning that it's this type of category where the objects, and we have objects, and well, it's a thin category where there are morphisms for any one object to other objects that are size either 0 or 1. And we can use this, we can use a notation of less than or equal to or included in here. This is a particular preorder category. This is another preorder category. So we have objects, we have morphisms where there's some sense of less than-ness, like less than or equal to. What that means in different cases is different. In some cases, it could be size. In some cases, it could be that it's included in another set. In other cases, it might be it's whether it divides it, right? Like here. These are preorders. And we saw some last time with that are total orders. Do you remember that? The total order? Remember this one here, a total order? This is a preorder, but it furthers a total order that we have this kind of linear ordering. But this is another preorder category. This is a preorder. Remember this one with cats, dogs, mammals, canids, animals? Remember this one? These are all preorders. We have a set of objects. From any object A to object B, there's 1 or 0 morphism. And there's no cycles. There's no cycles here, right? There's a notion of the morphism being like less than or equal to in this hierarchy. Some sort of order relation. But then there are some things that are not ordered, like these, right? Or that can be. Cats and dogs have no order in between them. It's not like dogs are cats or cats are dogs. So this is a preorder category. I know I'm waving my hands a bit, but you could figure out what composition is. And again, there's only one possible path, even if there's multiple ways of getting there. So it automatically commutes, and it's associative, and it's unital. Unital is each thing is less than or equal to itself. Okay. So we can have a category of these sort of preorder structures. Each of these is a preorder structure. I'm sorry, it's a preorder. But we just think of it as a dot. And these mappings are ways of relating those preorders. It's a relationship between this preorder A and preorder B that maps A to B in a way that preserves A's structure. Preserves the order. Let me give you a sense. That may seem very strange, but let me give you some examples. When I say it honors its structure, it preserves its structure. This is a structure preserving mapping here, okay? This should actually go to a dot. I don't know what happened. You should go to each of these, should go to a dot. So this would preserve the structure. Things that are higher up here go to things that are higher up over here. I'm sorry, that was a bad example. This would be another one. Things that are higher up here go to things that are higher up here. So don't get too distracted by this being reals, but imagine we had a mapping from natural numbers to itself where each number led to it being doubled. That would be a structure preserving mapping. Things that are higher up here in the source go to things that are higher up in the destination. Is this a monotone map? Are things that are higher up over here, according to set inclusion, map to things that are higher up in terms of their, we're just mapping according to the size of the set, the cardinality of the set. Is this monotone? Is it order preserving, in other words? Monotone means things that are higher up map to things that are higher up. It is monotone, yes. There's nothing What would violate it? How do we know if it's not monotone? Give me a map like this that's not monotone. If this mapped over to what? Let's say size mod 3, right? Then like 4 or 3 would map down to 0 again. And 4 would map to 1. And would that be monotone? No, because there'd be things further up here, like 3 is above 2, but the destination of it will be below where 2 goes to, right? Here it all maps over in a monotone way, in a way that's order preserving. Again, it honors the order. Is this the same order as this? No, but the mapping honors it. It's preserved its structure, some elements of its structure. Do you get that? So this notion of honor or order preserving mapping, that it honors its structure, means that if one thing is bigger than another over in the source, it becomes bigger than another in the destination map too. Are we comfortable with this notion? I might have another example. Yeah, here's another one. Is this monotone? Contains 2. You tell me. This is an interesting one. Think about it. So let's, when I say contains 2, it's a mapping according to whether or not the set that serves as the source for the match, the thing being mapped over, contains 2 or not. So like 0 does not contain 2, so it maps to false. 1 maps to false. 2 maps to true. Why does 2 map to true? Because it contains 2. Does 3, what does 3 map to? False. What does 0, 3 map to? False. Just follow the red. What does 2, 3 map to? True. Okay. What does 0, 1, 2, 3 map to? True. Right? Okay, so is this monotonic? So can you give me a counterexample? This is kind of a fun one.
So the empty set map to like any 0 was assigned as 0 or 1 there.
Well, does the empty set contain true? It contain 2,
False, right? False.
so it goes to false. Yeah.
How about like? But on the left side, there's a map from empty to assigned as 0, right? But false can map to false, right? False only map to 2.
So, well, here the ordering is different, right? Here it's a question. So this is mapping over true false. This is a category. It's a good question. This is a category where the objects are true false values, Boolean values, and this is implies.
Oh.
So does true imply false? No. Logic and logic. Does true imply false? No. Does true imply itself? Yes. There's an identity one. Does false imply false? Yes. Does false imply true? Yes. So in logic, this is kind of a Boolean category. Okay, but Jeff is right. This is monotonic.
I think it's because like once you have 2 in the set,
Yes.
any
superset also is going to have 2. So once you get it in there, and which is, if you have it in you, it's guaranteed to be in any superset of you, including yourself. And therefore, if you have true in you, it's going to be a true, it's going to be true. And then from then above you, it's going to be always true. So it's going to preserve the honor relation. It's going to honor the order relation. So do you get my sense that this is like preserving structure? It doesn't mean it's the same structure exactly, This is not the same structure as this. This is not the same, but it honors its structure as to a thing that's above in the source is mapped to a thing that's above in the target. Do we get that notion? And both are pre-orders, so that's the relevant notion of order here, the relevant notion of comparison. So we comfortable with this being order preserving? How about size greater than 3? Is that order preserving? Yes, because Jeff got the key point. Anything if you're greater than or equal to 3, all the ones above you are going to be equal to 3, right? Okay. Set size even, is this monotonic? No, because you could be of size 3, right? And you map to, well, sorry, you could be of size 2 and you map to true because you're even. And then you're the one that contains you 0, 2, 3 is going to map to what? False, right? So this one does not honor the ordering. Are we comfortable with this notion? So we call these maps monotone maps if they honor the ordering. Are we comfortable with that? Okay, if you get this notion, you are golden with a lot of understanding of category, okay? Because this notion of preserving order, preserving structure is at the very heart of categorical thinking. So I want to highlight this notion. Here we have a category where we've zoomed out. We don't care whether it's like this sort of thing or like this sort of thing, these sort of orderings. Each of these is some pre-order. It could be divided by 3, could be less than or equal to, by natural numbers. It could be set inclusion, some pre-order. It has pre-order structure. Each of these is some pre-order. One might be set inclusion, in other words, is with divide by, does it divide evenly by? Another is with in terms of the size of the sets, whatever. There's some pre-orders. Are we comfortable with this notion of a pre-order like this? Yeah, right? Like this, a pre-order. Each of these is a pre-order too. Let me get rid for future. Okay, now I'm in trouble. Okay, let me get rid of this. We don't need that. Okay. Smuggled in that. Okay. So each of these is a pre-order, shown both left as a pre-order, right as a pre-order. I think we're comfortable with pre-orders. So each of these is a pre-order, and these maps are monotone maps. This is what we have in category after category after category after category after category. We are going to look for the objects to be a certain type of thing where the maps, the morphisms honor the structure of the thing that's in there. So here, the notion of a morphism is not just any old mapping, not just some horrible scrambled mapping, not some entropic sort of splattering down of mappings. They're mappings that honor structure. Those are the morphisms. In category after category after category. The morphisms are things that honor the structure of what we talk about as the objects. Are we okay with this notion? And so let me ask this. Okay, if you say, well, okay, you want to be really, really picky and that's all you want for morphisms? Yeah, it's order preserving maps, not any old mapping. I want only the best maps, the order preserving. I'm exaggerating. Order preserving ones only are considered the morphism. Then I might ask you, okay, is there for every object, is there an identity morphism? So if we imagine we have a pre-order, is there a well-defined notion of an identity morphism on the pre-order that is a monotone map from it to itself? Yeah. What is it monotone? You bet it's monotone. Like this would go to this, 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 this would go to this. And is that a monotone map? Yeah. Things that are above go to things above. Things that are below go to things below. Are we comfortable with that? Okay. So you ever talk about like preorders and maps between, and that's what the morphisms are in this category. Okay. We're going to go through a lot of categories in this course, and it's always going to be that same flavor. Always going to be that same flavor. This is the flavor of category. Just as much as salt is the flavor of the ocean's water. This is the flavor, okay? So the objects will be different things. These may be vector spaces, and the maps between them will be order preserving or will be structure preserving things on these vector spaces, which are linear maps. Or the objects here will be monoids, and the maps between them would be monoid homomorphisms, things that honor that structure, preserve that structure, preserve the kind of monoidal rules of what combined with what yields what. It could coarse grain it, but it's preserving the essential structure of those rules. These things could be topological spaces, and here we'll have homeomorphisms between them. We'll have morphisms that preserve the structure of those topological spaces. These things could be, it could be a category of groups. This could be a group, this could be a group, this could be a group, and we'll have group homomorphism. These could be graphs, and we'll have graph homomorphisms. So we're going to give some examples of these, okay? So here's a graph on the left. You agree that's a graph? Here's a graph on the right, and I claim there's a homomorphism from this to this. What do I mean by that? I mean, if we had a map here, what mapping from A, B, and C, with the arrows following through accordingly, would be a homomorphism here? So it would preserve this structure in the sense of you could either map over and follow the arrow. Watch my words here. This is extremely important for the reasoning I'm using. Am I recording this? Yes, I'm recording this. Okay. For better for us. Okay. So what my reasoning is, I want a homomorphism. What this means is I can either map over first and then take an arrow out, the green arrow, or I could take the green arrow out of here and then map over and I have to get the same thing. Same thing, I can map like C over here and then take the orange arrow, or take the orange arrow here and map B over, and I have to get the same thing. So when I say it's a homomorphism, I'm saying that if I take the action in the source object, if I map over and take that action, the target object, it's the same as taking that action, the source object, and then mapping over. Are we okay with that notion? That's going to be, we're going to see this again and again and again with functors, with natural transformations. It's the flavor of these mappings. So what is a mapping of A, B, and C that causes this to be a homomorphism? Yeah, A to A, B and C to B. This is one graph, this is another. Are they the same graph? No, there's a mapping going on. This is not a map, this is not the same graph, but it preserves some of its essential structure. Do you see that? So arrows from A here on the left go to the place to which their targets are mapped over here. Their equivalent over here go to this place to which their targets are mapped. Let me ask you, so first of all, is everyone comfortable with this idea of this being a homomorphism, that if A goes to A over here and B and C go to capital B over here. So little a goes to big A over on the right, lower b and lower c go to capital B on the right. Are you comfortable with this being a homomorphism? That if we start in the source, we follow an arrow and then map, it's the same as mapping over and then following the corresponding arrow in the target, we have to get to the same place. Okay, so can you give me something that would not be a homomorphism and tell me why? Like what would be a mapping that would try to scramble things in a way that would be incoherent? It would not be well-behaved. That's what we're looking for. Well-behaved mappings. Ones that honor the structure. What would not honor the structure? What would be a nonsensical mapping here? Can you give me an example? It wouldn't be the one drawn here. Can you give me one that would be nonsensical? Let's suppose we were to map what? Give me one that's not a homomorphism. So I have A and B over here. Here we go. A and B. And in the target, we have, it's given. When I say it's mapping over, I'm not saying the right-hand thing is created by the mapping. What I'm saying is the right-hand thing exists and we're assigning arrows as we map them over. We're assigning objects as we map them over. There, okay. Okay, so we have an arrow here. We have an arrow here. We have an arrow here over on the right. And then we have 3 arrows. I happen to color them to show the homomorphism there. But if we had this, what would not be sensible? Can anyone say? What would be a nonsensical mapping? One that would not be a homomorphism, would not honor the structure. Well, here over on the left, we have 2 arrows here. You can see we have an arrow here and an arrow here, yeah. And then we have an arrow here and one like that. Maybe I've forgotten. Okay. So let's suppose, give me one that wouldn't be legitimate mapping. It wouldn't make sense.
Either C or B next to capital A.
Yeah, so let's suppose, to break the symmetry, let's suppose little a goes to big A and little b goes to big B. Why do I say that wouldn't be a homomorphism? Well, let's see. What would come about? Okay, we need to assign, okay, we know where little a goes, we know where little b goes. How about this arrow from A to B? Where would that go? Well, it would need to go from A to where? This arrow on the, so this arrow here, this here arrow, if we map little a to capital A and little b to capital A, where would this arrow need to go?
So
From A, capital A to itself. Is there an arrow? No. That would not be a legitimate mapping. It's not, it doesn't work. It doesn't add up. It doesn't honor its structure. The structure over here is this relationship where arrows come from. They're source and target. And we can't capture that structure here. We can't capture that structure. If we map, we claim the vertices, little a, little b, go to capital A. But wait a minute, we haven't honored the structure. We haven't captured where the arrow goes, because the arrow has to go from, its source has to be where little a goes, and its destination has to be where little b goes. So it would have to go from capital A, source of little a, to capital A, source of little b, and there's no such arrow. So it would not work, right? Right? Okay. Now, I'll leave it as an exercise to think about little c, but I think you see the reasoning here, eh? So this, are you comfortable with this notion of a graph homomorphism? Again, we're not capturing all structure. Okay, now I'm going to freak Jeff up. Okay, I'm gonna freak someone out who might not have seen it. Okay, so I'm gonna introduce a thing called a monoid. Okay, monoids are very important structures. But this is related to the points in the book about no objects and the fact that it's the morphisms that are the key points of focus in category theory, and where structure is encoded with, the composition of morphisms particularly. Okay, so this is going to be a category. It's going to have a single object. This is actually mentioned in the book, and this is why it's necessary to have a session which mentions this. So this is a category with a single object. We're going to call the object star. Okay. Don't get caught up in thinking it's some weird set. Don't get caught up in thinking it secretly has some elements. No. It's just a dot. It's just a dot. Keep your attention on the morphisms. There's two morphisms here. The identity morphism, which I've written ID sub dot, and one other morphism from the dot to itself. One other morphism. There's two morphisms in this category, the ID one and one other one. And there's only one object, so we know their source has to be that object and their target has to be that object. Are you comfortable with that? Are you comfortable with that? All right, Jeff, are you comfortable with that? Okay, now, remember I said the structure is encoded through the rules of composition here. That's the primary place we encode structure. So I'm gonna, remember, you get to choose for a category. When you specify a category, you have to be able to specify what are the rules. What are the rules for composition, right? Any two end-to-end morphisms, you have to be able to compose. Now, if you only have one object, all morphisms are end-to-end, right? Because they come out of the same and they go to the same one. Okay, so we have to be able to have any composition of the morphism. Some of them are given. So tell me one composition of morphisms that you know immediately what it is. By the axioms of category theory, you know. In fact, there's three you know immediately what they have to be. What are the three? Combinations of different morphisms, right? What are there are two morphisms here? So and they're all end to end. So any combination of them is end to end. So give me one that you know immediately what it is. You don't have to tell me because it's specified by the rules of category theory, by a category. Yeah, identity to identity is identity, right? It has to be identity to anything is that thing, right? Okay, follow that thought through. So identity to identity is identity. Excellent. That's the primary one I had in mind, but follow that thought through and you'll find two more. Identity in any morphism is that other morphism. So give me in either order, right? So give me another one you know by the rules of category, by the rules of a category, rules of engagement of category, the axioms specify what it has to be.
I don't say with any other.
Yeah, with one. The other one is one here. So identity and then one is one. One and then identity is one. Yeah. Okay. So the only one we get to choose, we actually do have to choose. What are our choices? When one is composed with one, we have two possibilities. Only one of them is a monoid. Well, only one of them is the one I have in mind right here. Mod 2 monoid. If this is the mod 2 monoid, what did one and one have to be? Identity. Because we're going to call identity 0. We're going to call 1, 1. And this is like doing, well, it's what?
It's 4.
It's actually adding 0 plus 0 is 0, 0 plus mod 2, right? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, right? This is like mod 2. Do you get that? What's the other possibility we could do as a separate monoid? It would be a different monoid. Which one is it? What could be our other choice of G after F? What could this be?
I'm thinking about the polarities, for example, plus and minus.
Yeah, where we interpret as times. Yes, this is a monoid. That's why John has
Yeah,
the monoids. Yeah. Yes, monoids. Monoid. Commutative monoid. That's right. Okay, but what would be another perfectly legitimate possibility be? It wouldn't be mod 2 monoid. It would be something else. What would it be? What's the other choice? I'm saying we have a choice for this one. What could this be? Remember, we can choose what the composition is. What else can we choose it to be besides ID star? Oh, what's the other possibility? 1. Like we could do that, right? Then it's like idempotent. Once you get you do 1 and 1, you get 1. Yeah, okay, fine. It's possible. That could be the rules of composition for a category. It's not the mod 2 category. Do you get a sense of this as mod 2? Do you understand why I call it mod 2? Sort of binary addition with 1 bit. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Do you get that? Are you comfortable with that? Are we good? What would it look like if we wanted to have mod? This is mod 2, right? Because we have 0, 1, 0, 1, 0, 1. Let's suppose we wanted to do mod 3. What would we need? What else? Well, we'd have one more. Suppose you were to design a monoid to have mod 3, to encode mod 3. What else would you need? The possibilities would be what? What are the possible values then? Mod 3. Mod 2, you can have 0 and 1. What could you have mod 3? What can you have mod 3?
We need 3 elements, 1, yeah, 2.
0, 1, and 2, right?
I'm thinking of morphism, like, so.
Yeah.
There's another.
Yeah, the elements are morphisms, right? This is why I thought it might freak Jeff out. He exhibits, placid behavior, but maybe inside he's deeply disturbed. The so-called elements of the monoid, they are elements of a monoid that this represents. They're morphisms. They're not objects. They're not like, we don't look in the objects to be like sets, here. The elements of monoid are encoded in the morphisms. In composition, it's like an operation on them. Do you get that? Like 1 plus 1 is 0. 1 plus 0 is 1. So if you were to have mod 3, what would 0 plus 1 be? What would serve as 0 there? What would serve as 0? Identity again. And then we need a 1 and a 2, just like Nastran said. 1 plus 0 would be what? 1. 1 plus 1 would be 2. 2 plus 1 would be 0. 2 plus 2 would be 1. Do you get that? It would encode ternary arithmetic. Are we comfortable? Well, yeah, it would encode mod 3. Are we comfortable with that? Jeff, are you comfortable with that?
Kind of.
Okay, yeah, I know it's kind of freaky. Okay. This is called maybe I shouldn't. Okay, so this is called the free monoid. I've only drawn 0, 1, 2, 3, 4 because I didn't want to make it horribly ugly. I know it's not pretty, but it takes a while for me to draw these things. 0, 1, 2, 3, 4, but imagine 5, 6. This is what's called the free monoid. And there's a deep notion of freedom here, but we'll get to that at a later time. But here, everything is as free as possible. So unless it's forced by the rules of categories, you'll have a new element here. So this encodes the natural numbers. This is 0, 1, 2, 3, 4. So if I add 2 and 3, I get 5. If I add 1 and 2, I get 2. If I add 2 and 1, I get 3. Where add is encoded by what? What serves the role of adding here? What serves the role of adding here? What are we doing? Like composition. Composition is how we combine these things. This is an extremely important notion. And it's a testimonial to the power, indeed the glory of categories. Okay, now I want to stretch you a little bit more. I know Jeff may want to run out of here.
Go back to the.
Yes.
Oh, the bottom row is identity.
Oh, that's weird. I don't look at that. I don't know. That should be 3. Oh my gosh. Thank you. You're the only one who's ever pointed that out. And okay. Out of black spot. Let me just try to rescue it from ignorant me. Okay. From a horrible loss of confidence. Okay. So let's go get that in. Okay. There we go. Okay. And then we'll color it nicely and you'll hopefully ignore the oh, come on. Where's the coloring? Okay, here we go. Oh, okay. There we go. There. Out of black spot. Okay. Now what I'm telling you is there's a structure preserving mapping that you can have between monoids. So this is encoding arithmetic of non-natural numbers with plus and 0 as the identity, as the neutral element in the monoid. It's the kind of thing you add to anything else, you get the same thing. Do you see why this is a category? Things just yearn to be identified as categories. Categories capture this inherent structure and thing. But I'm telling you, mappings here, we could have mappings that honor this structure. And I'm telling you, there's a mapping from the free monoid to the mod 2 monoid that honors the structure of this composition. Do you remember what that means? That means if we do an operation here, and then map over, we have to get the same thing as mapping over and doing the operation over in the target. So you tell me, what do you think 0 maps to? What do you think 0 has to map to? The identity has to map. It can map to identity. It's got to map to identity. 0 has got to map to 0. What do you think 1 maps to? If I want to take the free this kind of addition of natural numbers, monoid, it performs addition of natural numbers. We just call each of these a natural number. If I want to map that over to mod 2, what is 1 going to map to? What do you think? So 0 maps to 0. The star maps to star. That's just the up. 0 maps to 0. What does 1 map to? It's got to map to 1. What does 2 map to? 0. What does 3 map to? 1. What does 4 map to? 0. And it turns out this honors the structure. So let's just do a computation, right? Let's suppose I add 1 to 2. Well, maybe we'll start simple. Add 0 to 1. Does it? So if I do it over here, I do the operation here. I have 0 and I compose it with 1. What do I get? 1, right? And then I map that over to 1. Is that the same as mapping identity over here and then 1 over and composing them over here? So I want to ask, if I compose them here and then map over, is it the same as mapping each of the things to be composed over and then composing them here? So I'm asking that with 0 and 1. So 0 goes to what? 0. 1 goes to what? 1. And then I compose them over here on the right. I get what? What do I get? 1. But if I do them on the left, 0 and 1, I get what on the left? 0 composed with 1 is 1. And then I map that over, I get 1. Okay, does that work? Yes. Okay, now let's try something more adventurous. Add 1 and 1 here. What do I get on the left? Add 1 and 1, I get what? 2. Okay, map that over, what do I get? 0. Okay, now let's suppose I map 1 over to the right. What do I get? Okay, I map the other 1 over to the right, I get 1. And then I add them on the right, I get 0. Is that right? Okay, how about we add 1 and 2? Let's do it. Add 1 and 2. So I'm going to suppose I map 1 over to the right, what do I get? If I map 1 to the right, I get. If I map 1 to the right, what do I get? 1. If I map 2 over to the right, what do I get? 0.
0.
And then I compose them on the right, what do I get? So 1 and then 0 compose is 1. And now let's do them on the left. I compose 1 with 2 on the left. What do I get on the left? 1 with 2. So I get 3. Should have had a 1 and 2. 3. And then I mapped over, I get what? Map 3 over, I get
Again, 1.
1. Okay, it works. And this is a general mapping that honors structure. Do you see why I say it honors structure? Is it the same structure? Does it encode all the structure? Does it encode all the rules? No, it doesn't. But it's compatible with capturing the essential structure. Its rules are consistent with their coarse-grained version, but they're still consistent with what's over here on the right. Right? Just kind of glomming certain things together. Do you get that point? It's capturing the essential structure of the situation on the left and staying true to it while coarse-graining things, while combining, clumping some things together. Do you get this notion? Kind of like if someone looked out at a scene outside and they drew a very blobby version of it, like a kid would draw a blobby version of things, you can kind of recognize, they captured the essential structure of the situation. Like elephants draw things, they'll draw a tree or whatever with their trunk. You ever seen that? They draw it with their trunk. And it's like an abstraction of the situation, and they've stayed true to the situation. So what I'm saying is there are monoid homomorphisms here. We said this earlier with graphs. Do you remember this? I'm saying there's a category of graphs where graphs are objects and graph homomorphisms are the morphisms. Here, there's a category of monoids where monoid homomorphisms are the morphisms, right? Only monoid homomorphism, not any old scrambling. Are there some things that would not be homomorphisms here? Some mappings that would try to scramble things and wouldn't make sense? They don't capture, they're not well-behaved mapping. Can you give me a not well-behaved mapping that would not be a homomorphism?
Identity, and other 1, 2, 3, 4 maps 1.
Identity to,
So,
identity to identity. 1, 2, 3, 4, up to 1.
mhm.
Would that work? I think it might work.
Essentially, it's a binary.
Right. Right. I mean, certainly if you said 0, 0, 1 maps to, so 0, if you said identity maps to 1, then you'd be all in trouble, right? And 1 maps to 1, and you'd be all in trouble. If you said like 0 maps to 0, okay, fine, give me that. 1 maps to 0, right? And 2 maps to 1. There'd be no way to get to like 2 on the right, because like 0 maps to 0, 1 maps to 0. So like you couldn't add 1 and 1 to get 2 on the right, or to, yeah. So you couldn't add 0 and 1 to get 1 on the right. Maybe I should give that as a little exercise. Okay, so we're kind of out of time, but I do want to say the same notion. This is a key central feature, defining feature of category theory. We have this idea we can define particular categories as categories, but then we can zoom out and have categories of these things where the maps between them honor the structure. And they're only those well-behaved maps, namely the ones that honor the structure, that preserve the structure. Do you get this notion? Like they are monoid homomorph, the objects are monoids and the morphisms are monoid homomorphisms. There are these well-behaved mappings between monoids, not just scrambling. The objects are graphs and the morphisms are graph homomorphisms. The objects are causal loop diagrams and the morphisms are causal loop homomorphisms. The objects are vector spaces and the morphisms between them are structure preserving mappings, which are linear maps. The objects are preorders and the maps between them are monotone maps. These things we saw earlier honor structure. Do you get this notion? This is throughout. This is the standard thing of how we use categories. And it's kind of weird that we start with set. I know set is very familiar to us, particularly as computer scientists, but this is a situation where there's really no structure to be honored. And this is why I started with this. There's no structure. There's no structure to be preserved. So it's any old function. It's any stinking function. And that's not in general the flavor. That's like a kind of, that just gives an oversimplified notion. In general, we want these mappings to honor the structure. And set has virtually no structure, has essentially no structure. These things have structure, and we ask for our morphisms to preserve, to honor that structure. Are we okay with this notion? This will be throughout. Same thing with dynamical systems, right? There's a discrete dynamical system here going from state I to state A to state B to state C to state D. It goes in this loop after this. Imagine this is a little thing that goes between these states. It starts in state I, the initial state, and goes to A, B, C, D, A, B, C, D, A, B, C, D. Could that be a dynamical system, a discrete dynamical system? Yeah, it's a bit like a clock going around, right? And I'm saying this is another dynamical system which starts in state capital I, goes to state R, the recurrent state, and it just stays in R. It just sort of hangs there, going, gong, 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 gong. And what I'm saying is this mapping between them is a homomorph. There can be a homomorphism. What would the homomorphism have to be? Well, I've written it down there, but I'll cover it up so you could tell me. What's the homomorphism? What do you think? What has to go to what to honor the structure? That's right. Can you give me one that does not honor the structure? That's nonsensical. It's just like a sloppy spray of assignments that has no internal consistency. Give me one that would be not honoring the structure.
Anything other than the I mapped to I?
Yeah, so if I doesn't map to I, there's no way to get to I here. And so there'd be
Map,
and nothing can get to I. So if we mapped I to R and then we map like A to I, like that doesn't make sense because here you can go from I to A, but here you couldn't go from the target of I to the target of A, right? So it wouldn't make sense like to put all of these things A like up at I and I to I, because you'd have to be able to go from capital I to itself, and you can't here. Mind you, this is not a category. What I'm showing is not a category. There's no secret little identity morphism. No. This is a dynamical system. We're just drawing it out like that. So don't get caught up there secretly identity ones. No, there's just, if you're a capital state I, you go to capital state R. So it wouldn't make sense to map like I and A over here. Give me another one that doesn't make sense. Well, A and C.
B to I, and B, C to R.
Yeah. That's right. So, a lot of it has to do with you can't get back from here to here, etc. So I think you get the point. Like, there's a notion of structure here, and we can have mappings that don't just duplicate the structure, but they honor the essential features of it, even while they may stretch it and so on. They honor it. And this is the key notion, and it's going to be key for topology too. We capture the essential structure, even if we abstract in a lot of things. It's key for stock flow diagrams, right? With stock flow diagrams, we have homomorphisms between stock flow diagrams. These are stock flow diagrams, and we have a homomorphism that can like collapse, say for a system structure diagram, collapse the exposed in the I stocks into one stock or something like that. Or it collapses the asymptomatic infectives in the symptomatic infectives into a single stock, right? Or it collapses the folks, this wouldn't, so maybe it collapses male and female susceptibles into susceptibles, male and female infectives into effectives, what have you. Okay, so if you can get those key notions that I've tried to emphasize today, you'll do really well with category theory, because these lie throughout. I think I'm going to stop